Hello everyone, I am Maria Juliana Disgate, and today I'm very excited to share with you the difference between passive and active noise barriers. Let's start by defining what are noise barriers. Also known as sound barriers or acoustic barriers, these are structures, methods, or techniques designed to absorb, reflect, or cancel the transmission of sound from a noise source to the environment nearby. We will consider noise unwanted sound because it degrades the comfort level of living spaces, but just to be clear, both sound and noise are similar in acoustics when propagating through air particles. Now let's see why are noise barriers important. I have grouped all the reasons in three big groups. The first one is health and well-being. So under this first group, we can find hearing protection because prolonged exposure to high noise levels can lead to hearing loss. So noise barriers help mitigate this risk. The second is stress reduction because continuous noise pollution can increase stress levels, leading to mental health issues such as anxiety and depression. So noise barriers can create a quieter environment that promote mental well-being. The third reason is sleep quality because noise pollution can disrupt sleep patterns, leading to chronic sleep deprivation. So by reducing nighttime noise barriers, help improve sleep quality and overall health. The second group is environmental impact. And here we have the first reason is wildlife protection because many animals rely on sound for communication, navigation, and predator-prey detection. So noise barriers help protect wildlife from the disruptive effects of human-made noise. And we also have ecosystem balance because reducing noise pollution helps maintain the natural balance of ecosystems supporting biodiversity. The third big group is economic benefits. In here we have property values. We know properties located in quieter areas tend to have higher real estate values. So effective noise barriers can enhance property desirability and market value. And the second one is productivity because reduced noise pollution can lead to increased productivity in workspaces and educational settings like schools, universities, because they minimize distractions and create a more conducive environment for concentration and learning. Let's consider a very common scenario um, that we face daily. So let's think that we are in a big city walking in a main street and we start hearing multiple noises simultaneously. Um, let's consider, for instance, traffic noise, the vehicle horn, construction noise, aircrafts flying, dogs barking, police and ambulance sirens, people talking loudly, music being played, and then some negative feelings start to come up, like stress, anxiety, irritability, fatigue, difficulty concentrating, or even thinking what you are going to do next, frustration, just in general a sense of discomfort. So, noise barriers have been developed to address the growing problem of noise pollution, particularly in urban and industrial areas, because the need of protecting our ears and well-being from excessive noise became essential. The human ear responds to frequencies in the range of 20 Hz up to 20,000 Hz or 20 kHz. So, before we start with the two types of noise barriers, I would like to share with you the types of acoustic noise that exist in the environment. Um, One is caused by turbulence and is totally random. So turbulent noise distributes its energy evenly across the frequency bands and it's referred as broadband noise. Examples are low frequency sounds of jet planes and impulse noise of an explosion. Another type of noise called narrowband noise. Um, concentrates most of its energy at specific frequencies. So this type of noise is related to rotating or repetitive machines. It's periodic and or nearly periodic, and examples of narrowband noises include the noise of internal combustion engines in transportation, compressors, and refrigerators, also vacuum pumps used to transfer bulk materials in many industries. Okay, now that we are more familiar with acoustic noise and different types of frequencies, we can start talking about the two approaches to controlling acoustic noise, passive and active. The traditional approach to acoustic noise control uses passive techniques such as enclosures, barriers, and silencers to attenuate the undesired noise. However, these techniques are relatively large, costly, and ineffective at low frequencies. We will consider those below 500 Hz, making the passive approach often impractical. So that's why we need active noise control or active noise cancellation, and we will start with passive. The first technique that we will discuss today is passive noise control or noise isolation. The idea here is that an incoming sound wave gets absorbed or reflected by a physical barrier, and then the transmitted sound wave gets reduced or completely blocked. Materials commonly used in passive noise control may include porous surface material, acoustic foam, mass-loaded vinyl, mineral wool, fiberglass, acoustic ceiling tiles, soundproof drywall, rubber and cork flooring, acoustic glass, and carpet and underlay. These materials work by either absorbing sound waves, blocking their transmission, or reducing their reverberation within a space. Passive noise control can be easily found nowadays in three big groups: residential, commercial, and industrial solutions. So from homes, home theaters, classroom, offices, conference rooms, auditoriums, recording studios, and restaurants, you will find passive noise solutions. For instance, here we have a soundproof door. By adding layers of sound absorbing materials within walls, ceilings, and floors, or in this case doors, you can improve the overall sound insulation and reduce noise transmission between rooms and floors. In offices, it's very common to find polyester fleece material and just acoustic glass. And then it's very common in factories to have enclosing noisy machinery within a soundproof casing. It's commonly used for generators, compressors, and really heavy machinery, just to reduce the noise levels in the surrounding environment. Applications of passive noise barriers can be easily found in open spaces through absorptive noise barriers, especially designed for roads, highways, and railway corridors. It consists on a post and panel wall system made of noise absorbing material, and it's designed to reflect or absorb sound. We can also find acoustic gabions walls, which are an excellent solution for reducing noise from traffic, loud neighbors, and industrial noises. And also, we can more recently, we can find acoustic living walls, also known as noise screens. So typical applications include industrial and residential boundaries, locations adjacent to transport routes, as well as commercial premises that need a heavy-duty, long-life solution that delivers outstanding acoustic performance, while sensitively considering the visual impact in the environment that sits. Okay, so far we have finished with passive noise barriers, and now we will jump into active noise barriers. And in here, the most used and popular technique is active noise control or active noise cancellation, opposite to passive. In here, we change the sound field in an electronic way, and for that, we need electroacoustic transducers like loudspeakers and microphones. But for some applications, we can replace microphones with tachometers and accelerometers. So today I wanted to show you the example of the ANC system in a duct. We can find this in the paper reference here by Senhua. I feel that this example it's great to understand how ANC works. So let's start. We have a noise source. So let's think that a considerable amount of broadband noise is produced in this duct. And we have our noise loudspeaker, and we are getting our primary noise signal propagating from the noisy loudspeaker until the position of the error microphone. This distance is going to be known as our primary path. And this input signal that we call reference signal is going to be measured by our reference microphone, and it will feed the ANC controller with that unwanted noise. Inside of the active noise controller, we have a digital filter and we have an adaptive algorithm that we will see in a future lesson. But what happens here is that the adaptive algorithm, it adapts the coefficients of the input signal, so we can get the anti-noise signal as the output of the filter. This anti-noise signal is nothing but the primary noise signal with the phase shifted. So we have the same sound wave, same amplitude, but opposite phase. The canceling loudspeaker will take that signal and reproduce it into the duct. So this secondary noise will propagate from the position of the canceling loudspeaker until the position of the error microphone, and we call this distance our secondary path. Okay, so what happens next? When our primary signal meets our secondary signal, the principle of superposition or destructive interference will occur. We have two sound waves with equal amplitude but opposite phase added up in a closed enclosure small space. So they will cancel each other out, and then we have our error microphone. This error microphone is crucial because we will always place this error microphone at the position where we want to get silence, the quiet area, the residual noise going close to zero. So in this case, for the duct example, it's the end of the duct. This is where I want to see the change from the noise signal to no noise, to quiet or silence. So the error microphone will measure our residual noise signal or our error signal, and it will feed the ANC controller with it, with that residual noise. And this process is iterative and adaptive. So it will perform until the error signal becomes zero or very close to zero. It has to get minimized very close to zero. So when this error signal gets very close to zero, because both primary and secondary noise signals are very similar, then it will start to adapt because there's nothing more to compare and to adapt. So that's where it finishes and goes to an stationary point. Active noise control systems are run on dedicated digital signal processing hardware, DSPs, designed to run this task efficiently and with minimal system latency. Why? Because the system has to capture the noise signal, generate the anti-noise signal, and send this anti-noise signal back into the system to cancel the primary noise signal in a short period of time, because the speed of sound is 343 meters per second. So As DSPs became smaller, cheaper, and faster, ANC became more popular and more used in commercial solutions. We have here two examples of applications for ANC. We have vehicle inside the vehicle cabin. It's very common to find active noise control for traffic noise, road noise, um, also for the engine noise. But when it comes to combustion engines, but also we can find ANC in electric vehicles. And then we can also find ANC in canceling earbuds. Earbuds implement both passive and active noise control techniques, so it's a hybrid system. And beside these two, we can also find ANC in chips and home appliances and many more scenarios. To conclude this lesson, I wanted to highlight that understanding the difference between active and passive noise cancellation, it's very important. Both technologies aim to reduce unwanted ambient noise, but they do so through different methods. So just wanted to remind you that active noise control offers a better performance um, at low frequencies, and passive noise control offers a better performance at high frequencies. However, they can be implemented together. They can be used together and they make a great combo. That's all for me. Thank you so much for watching. Now please stay here because my friend Magdi, he comes next and he will explain metamaterial resonators and panels as passive noise barriers. Bye.